Okay, now we are officially recording, and about 40 students are here. So, okay, let me just in the briefly discussion about the last lecture. Last lecture we said, okay, for example, we have maybe a axial bar, something like this. It could be bar, rod, element. We said is under the force, for example, P, and then it's under the L and cross sections A, material losses of modulus E, and the formula we obtain this one, right? We obtain the, how can we find the elongation? For example, if this is the elongation, right? And actually this bar, it would be something like that, right? And if you look at this element, in the free body diagram, you have P, and this reaction here, P, right? Something like this. And then we find delta. But the question, okay, the question is, what happens if, for example, we have, again, maybe the same elements, right? Something like this, and this force. And what happens if you have some additional force here? Maybe P2, if this is P1, maybe somewhere here, right? Or maybe what happens if we have the element, but with two type of material. Maybe this is E1, this is E2, right? Under the force. Or maybe what happens if, for example, we have with two cross sections, maybe one cross sections here, and then this one, we have maybe this force, different maybe force here, right? And so, okay, today we wanna talk about this, which means we find this formula. We already know this formula, and this is, we can use this one just only for the one specific segment, right? So something like this. We have in this segment, we have just the one force here, and this is the length of that. And also during this segment, we have just constant cross sections and the same material, right? And now today we want to talk about, okay, if you have, for example, structures, actual structure under the actual forces with different type of the length, different segments, different cross sections, different losses of modulus, then how can we solve the problem, right? So let's just start this. Let me just, for example, let's write distinct segments, right? So first of all, I wanna just I don't want to show the example first. I wanna just some parametric things, the figures, the general figures with the several segments and with the parameters A, L, and E, right? So let's just assume we have something like this. Let's assume we have, for example, let's see. For example, we have 3 segments, right? Let's assume we have something like this. And there is a force here. Let's just use just one force, just force P, right? And let's see, this point A, this is point B, this is point C, this is point D, and those are the dimension of that. Let's see, this is LAB, LBC, LCD, and also this is a cross section, so it's AB, and this is might be losses of modulus. This may be the BC. It has another last of modulus. This is ACD. I'm just writing the very general or arbitrary segments, right? Those are just connected to each other. So, okay, first of all, okay, now we can see we have 3 segments, right? 3 segments. First of all, we should use statics to find the forces in each segment, right? So now, just forget everything about the material. Let's just back to the statics, right? ME304. So we want to find, first we want to find the force in each segment, and then using that force, we want to find maybe the elongation at that segment, right? And then I want to discuss about that. So let's first focus on segment AB, right? Just first focus on the segment AB. Let's just make a section somewhere. Just let me just the same as the statics, like let's, for example, this is here, just like, let me write, this is FAB, right? Somewhere. This is the, okay, just something like that, right? Just I make a section somewhere in the segment AB, right? So equilibrium. So this is for case AB, right? Against the summation of force in direction of x0. So we have minus FAB, this is internal force, plus P equals 0. And then FAB equal P. Okay. And now, okay. So we discuss here about this formula. We said you can use this formula for each segment with the just cross section, the last modulus, and L. Now just focus on only segment AB, right? So we have segment AB now is something like that, right? This is segment AB, right? Just this is AB. Yes, only segment AB is under the force FAB and FAB here also, and we know FAB equal P, right? Just for this segment, you don't look at this. Just for this segment, let's write the formula for elongation, and then delta BA. What's the formula? FL over AE. But let's write the index. AB, AAB, and EAB, right? Just I put the index. So one index should be discussed. So this is the force AB is P, LAB we know, EAB, AAB. For BA, we can write BA or BA, something like this. Let me discuss about that. Or we can read it, which means, okay, if you have these segments, right? If you have these segments, using this formula, we can find the elongation. For example, if this is point B, right? This is point A. Elongation, right? At point B respect to point A. This index, something like, you can write BA or B over A. It's up to you, right? So now just we focus on these segments, right? If we mapped with this, let's just back to this one. Let's look like these two, right? Just we have these segments, and we can draw a segment like that. And this delta means this deformation respect to this point, right? We assume this point, for example, fixed, and this is the elongation for that. And now for this segment, let's just assume, for example, this one is fixed, right? And is already actually is fixed, right? Point A is fixed, right? And then we find elongation at point B, right? So now is everything is good. We have length, we have velocity of modulus, we have A, right? So this is for AB. And now let's make a section here, for example, for BC. Let's draw the free body diagram and first statically solve this one and find the force in BC. Let's is BC. For BC we have like that, right? Let's just make a section somewhere in this section. We have force P. This would be the F B C, right? Summation of force in direction of x0 would be minus FBC plus P equals 0, and then FBC also equal P, right? So, okay, it looks like this. We have something like that. For example, this is just segment BC, right? We can write FBC, FBC, and then, okay, we can delta CB or C respect to B, FBC, length of BC, A of BC, E of BC, right? So what does that mean? Which means we find the deflection at this point, respect that, this point, which means just this individual segment, right? So we want to just focus segment by segment. And then at the end, I said, how can we find the total elongation or elongation at some certain points, right? Let's just focus on one by one segments, right? So this is for BC. The last one is only just this segments, right? Segment CD, make a section somewhere there. So section CD. So let's just make sections. Yes, for example, FCD. This is the segment CD. Sorry, it's just P here. Summation of force in direction of x0. And if FCD plus P, and then FCD is P, right? That's a force. So, which means now we have this segment. This segment is F CD. This is segment CD, right? FCD, we already it. And then delta DC or D respect to C, any index you can use, that's fine. FCD, LCD, ACD, ECD, right? Segment by segment, right? So, which means now we can find, if this is point D, this is point C, for example, we can find the deformation D, elongation D respect to C, right? Here we can find the elongation C respect to point B. Here we can find for point B respect to A. Okay. So, and now let's back to this figure. Okay, and now just let me ask a question. Okay, we find the elongation B respect to A, we find the elongation C respect to B, we find the elongation D respect to C. Okay, and now for this point D, just at the end of this bar, end of this structure, how can we find the total elongation at this point? How can we find the total elongation at this point?
Read the sum of them.
Some of them, right? Because, right, some of them, thank you. Because we for this segment, we assume this is fixed. We find that the elongation is relative this. For this one, we assume this is C, then we find elongation of this, which means this point C also moved. And for this, we assume this is constant, is it fixed? And actually it's fixed, and then we find B. So which means B moved, C moved, and D moved. So then we can find the summation of that. So therefore, for here, let me write it here. So then the total delta D would be delta BA plus delta CB plus delta DC. That's elongation at point D. So now let me, at point D, let me ask you another question. How can we find the elongation at point C, the total elongation at point C? So, okay,
solve for B.
Solve for?
Would it be the elongation of BA plus CB?
Exactly, elongation of BA, because this is move, and elongation C respect to B, right? So for delta B, we can write delta, sorry, C, we can write delta BA plus delta CB. And for the last one, just delta B is only just this one, delta B equal delta BA, right? Because A is fixed. Delta B would be delta BA. So, and also, so, but the more important things is the point at the end, the delta D, right? Because right now we have something like this, right? We have something like that, right? So this is point D, this is point C, this is point B, this is point A. So this point, and we have a force here, right? This point, one is elongated, so this one is called the total elongation, right? So this one would be delta total also, and which means the maximum elongation happen here. So then if you have allowable deformation, we can compare with this one, because this value is greater than any other value, right? Delta D is greater than C and greater than B, right? This is a one end, right? So in future, if we ask to find, if you said, okay, find the delta total, means you need to find this one, which means find the delta for each segments and add each other. But if I wanna find the elongation at some specific point, I let you know. I let you know, okay, find the delta at this point, right? Or find the delta at this point. Then you can refer the other things. But if we said find a delta total means just delta at this end. So guys, regarding these things, this is, do you have any question regarding this? It's one of the important things in the material for the actual elements on the actual forces. Does it make sense to you?
Yeah, it makes sense.
So, okay, So let's go to the example. Let's go to the example with several forces. So, okay, let's go to the, if no question, let's go to the example. Okay. So in the example, we have, let's see, we have this bar. I'm going to solve this example step by step. So let's see if we have, okay, we have one force here. This force is 50 kilonewton. I have another force here. This force is 75 kilonewton. I have also here the force path in this direction, 100 kilonewton, right? So guys, let me, before writing the dimensions A and E and something like that, if you just take a look at that, how many segments do we need to solve this problem?
One.
One, but cross section change at this point. So this is not a uniform things.
2 segments, no?
2 segments, okay.
Three.
Three is right. Why 3?
You get each of them separately and then you get all of them together.
Yeah, 3. Okay, so let's see. So 3, okay, this is one is A, right? This is C. Here, okay, CD is 1 segment, right? From D to C, it's just length area and there is no force. From C, we are not able to consider CA as a 1 segment because C to B, after this point, we have a new forces, right? Which means just consider at the beginning, once we make a sections to find the forces. If we make a section here, we can find the internal force. Here, we can find the internal force. But there, if we make a section here and here, these 2 sections, we have a different forces, right? Because at this point, we have a new forces, right? So if we make a section here and summation of force in direction of X, then we have 1 force here. But then at this point, we have a new forces, which means we should rather consider this one as a new segments, right? Because if we make a section, here's the force between these 2 points is different, the force between these 2. Therefore, we assume this point as a point B, so we have a 3 segments, right? So, okay. So does it make sense to you? Why we pick 3 segments?
So the right side of that segment is going to be the 75 kilonewtons, and then the left side is the 100, right?
No, 75 just at this point. 100 at this point, at this segment.
Okay, so between B and C,
there is nothing.
There's no force?
No force here.
Okay.
Okay, now let's just go segment by segments, right? Let's just go segment by segment, because here in this work, you know, the first steps we find the forces, right? And so let's go step by step, find each force, and then base internal force, and then based on that, find the relative elongation, and at the end, so in this problem, it asks to find the total deformations. So in this problem, find the total deformation or elongation. The other thing also E, elasticity of modulus, we have the same material for all of them, 70 gigapascal, right? So please just, yeah, just focus on this problem. It's very, very important. Okay. So let's just first, maybe just this segment, just make a section somewhere here. Make a section between D to C, anyway, right? So then we have, just now we are in the statics, okay? We are in the statics, just 50 kilonewton, 50 kilonewton. And this one is, let's see, for example, P1 or FCD, anything you can just write. So, and okay. Summation of force in direction of x0. You have negative P1 plus 50 equals 0. P1 is 50 kilonewton, right? So now let's find delta. So delta D respect to C. P1. Oh, I forgot to write the dimension. Let me draw the dimension also. Dimension for the segments. Okay. This is 1.5 meter. This is 1.25 meter. And between A to B, 1.75 meter, right? Okay, and let's just set this is, for example, L1, this is L2, this is L3, right? Okay, for DC, P1, L1, A1, E1. Okay, we need also cross sections area. Let's cross sections. For CD, let's say CD would be 500 millimeters square. And BC and AB has the same cross sections. AAB, ABC would be 800 millimeters square. Okay, I'll use a different color just to see. So, and now just let's solve together. 50. What is L1?
1.5.
Okay, let's do something before L. For the 50 is kilonewton, let's just write based on Newton everything. Just multiply thousands, right? So L1 is, you said 1.5, right? A1, what is A1 here?
$500
500. The area, cross-section area here, it would be 500. 500 millimeter square, but L is based on meter. Let's the same unit. L is based on meter. Let's just A1 also based on meter. Just write 500 times 10 to negative 6, because each millimeter is 10 to the negative 3. And since it's millimeter squared, we have 10 to the negative 6, right? E gigapascal, 70 times 10 to the 9. 10 to the 9 means gigapascal to pascal, right? Pascal is Newton per meter square. If we solve this one, the answer would be 2.142 times 10 to the negative 3 meter, or 2.142 millimeter, right? Does it make sense?
Yes.
Okay, now section CB. Let's make a sections. Let's make a section somewhere here between C to B, maybe. That's just a static, right? You remember in the statics, once we wanna
Hey, Professor.
analysis the beam, make a section. Yes.
So if the object is connected to on the left side, can we assume that P is the force on the right side?
What you mean we have here?
Because the whole object is connected on its left side to the wall.
Yeah.
So can we assume that the force on the right side of the segment is going to be our force?
This force here, you mean?
Like 50 kilonewtons equals P1, where you did the summation.
Yeah. Don't be confused about the sum, which point is fixed. Just go segment by segment to find the internal force of that segment.
All right, I was just seeing if there was a faster way, that's all.
Yeah. For example, here, you know, we should find in each segment the internal forces, right? This force, right? And then it doesn't matter here we have a support or there. Just go segment by segment, right? Does it make sense? Yeah. It look like the, it look like the statics, right? It look like the statics, just if you remember, we have, for example, beam, something like that, right? And then we have some forces, different forces maybe, right? Then just we make a sections there, if you remember. And then it doesn't matter where should we have a support or reaction. Just we should make a section between the forces. We have force here, we have force here, something like that. And now the same as here, we have some force here and the force here. Just we should make a sections between the force, and the between the force means the segments we picked, right?
I get the statics. I was just looking for a faster way to calculate it.
No, yeah, just a step by step. Okay, how can I? Okay, I just, let's see. It's sometime okay, it's let's. Let's see. Okay, now we got it. Okay, so let's go for section segment CB, right? For segment CB, let's have there, right, and sections. We have 50 kilonewton here. What else? We have 75 kilonewton here, right? And that's the internal force. Let's just denote P2, for example, right? Summation of force in direction of x0, negative P2 plus 75 plus 50 would be equals 0. P2 is 125 kilonewton, right? Okay, now let's find in this segment C respect to B, right? This is point C. So delta C respect to B and P2L2, A2E2. Let's just now go to the figure. So just I want to ask you, in segment BC, in segment BC, we already find the force, right? What is the L? L in this segment is?
1.25.
1.25. What is the cross sections area?
800.
800. So, okay, now we have all things. P2 is 125. Let's multiply 1000 to Newton. L is 25, right? 1.25. A is 800 times 10 to the negative 6 to change to meter. E is 80 times 10 to the 9, right? The answer would be 2.79 times 10 to the negative 3 meter, or 2.79 millimeter, right? So let's go to the last segment. Last segment, then first statics. Just make a section somewhere between B to A. So let me sketch the drawing. So we have this here. We have this there. This is point B, point C. This is 75. This is 100 kilonewton, 75 kilonewton.
Professor,
Sure.
real quick, wasn't the modulus of elasticity the previous one 70, not 80?
Modulus of elasticity is the 80.
80? Okay.
Yeah, 80 gigapascal.
Yeah, originally you did write 70.
I did 70?
I think in part one of this.
Sorry, is it 70? 70? It is 70, right? Let me check in the previous, oh yeah, 70, right? I wrote, yeah, thank you, 70. So it is 70 here. So okay, and delta B, okay, let's summation of force in direction of X, negative P3 minus 100 plus 75 plus 50. What's the answer? Is 25, right? P3 is 25 kilonewton. Okay, then the last one, delta BA. And now I wanna ask you about, so we have P3. Let's see what is, okay, for segment BA, what is L?
1.75.
1.75. What is cross-section area?
800.
800 exactly. And Young's modulus is 70, right? It's constant for all of them, which means we have the same material, right? Now let's just substitution. Okay. 25, let's multiply 1000. L3 1.75, right? 800 times 10 to the negative 6, 7. Yeah, I saw something in the chat. Let me just write the answer, solution answer of this, and then I answer your question. So 10 to the negative 3 meter equal millimeter, right? That's for third segments. So there is something, RE should be 70. Yes, the RE is 70, not 80. Yeah, I fixed it 70 for all segments. Okay, guys, so if you wrote this, then let me now just go to the page.
For the total, what do we just add them all up?
Yeah, what value we need? We need the total. We want to find total. So total means this point, right? So we need this delta. We should add these two. This value, the second segment, and the third segments, right? So delta total would be delta BA plus delta CB plus delta DC 0.781 plus 2.79 plus 2.142, then 5.713 millimeter, right? This is delta total, and also it's equal delta D, right? At the end, as we discussed. Let's just find also delta C and delta B. Also, okay, the purpose is this one. This is very important. But let's just find delta C and delta B. What should, okay, for delta C, let me go to the page figure. For this point. For this point, what should I do to find the elongation at this point?
You just subtract the delta D, right?
No, we just
From
delta
the total.
CB plus delta BA, right?
Yeah.
Yeah. Delta CB, because we find the delta for C respect to B and find the B respect to A, relative. Just delta CB, delta BA. Right. Delta C would be delta BA plus delta CB would be 2.79, or yeah, you are right. Maybe this one minus this one. This is good, but yeah. And delta B only be relative to A, right? Just 0.78 millimeter, right? That's about this problem. Does it make sense to you? Let me know if you miss something. I can go over, I can write it. Does it make sense?
Yes, it makes sense.
So look at these values, these three values, right? This 2 is 2, this one is 2 is close 3, this one is 0.7, right? The reason is, you know, this is for the last segment. And in the last segment, if you look at here we have this force 50, then add the 75 force in this segment. And then here in this segment, we have the force in opposite direction, which means this force could be cancelled a more amount of this force, right? Which means the force would be just 25, right? Then, you know, in this segment, we find only 25 because of this reason, right? 50, 75, and 100 in the opposite direction. Then the total force here in this segment will be 25, and because of that, so we have a small amount of the elongation in these segments, in the third segments, right? That's a reason you can see, right? And so, okay, guys. Okay, let me